Hello everyone, and welcome to the Newton's second law for rotation post-lab, in which we try to create a math model that is like Newton's second law, net force is mass times acceleration, but for rotating objects, rigid objects rotating about fixed axes. So what we did in this lab, right, was that we calculated a torque and measured an angular acceleration, right, and kind of changed the torques and measured the angular accelerations as we went. Right? And this took a lot of calculations to get there, but right, it was very doable. And then you ended up making a graph of torque in Newton meters versus angular acceleration in radians per second squared. And hopefully your graph looked like that. Right? A nice linear graph that went through 0, 0. Which means, what is the relationship between the torque and the angular acceleration? Well, much like force, net force, and much like net force and acceleration linearly, they are proportional to one another. So if your object is angularly accelerating twice as much, it will require twice as much torque. If you put 3 times the torque on an object, it should accelerate 3 times as fast. Right? Again, very similar to net force and acceleration linearly. So then let's make a math model out of this. The y variable is, of course, torque. And that equals your slope. If I can show you some slopes here from the past, we have a few. All right, so here's a few groups. What do we got here? We got 6 data points, half dozen data points. If you look at them, yeah, they're small numbers, okay, but they're fairly consistent numbers. Right? Do you notice that they're all within just a few, right, of these? What are these? Tenths, hundredths, thousandths, 10,000ths. They're within a few 10,000ths of whatever the units are, of one another, right? Even this one, which is 0.006, right? And this is 0.00588, right? It's not off that much. They're off by, not even a percent, less than 0.5%, actually, of one another. If we take an average, it works out to be 0.0059. Okay, so that's what I'm going to use in my math model, okay, which seems to be pretty close to what all of you got, right, in the actual lab, and so should be believable for you. Now, let's talk big messy units. Rise over run, of course, because it's a slope. Units of rise, Newton meter. Units of run, radians per second squared. So it's a Newton meter for every radian per second squared. Okay, well, what does that mean? Well, again, remember, as always, slopes are rates of change. When you change the x variable, how much change do you get in the y variable? So for every 1 radian per second increase in the angular acceleration, the torque increases by 0.0059 Newton meters. Now, again, it's a small slope, but that's because we were talking about really small torques and actually fairly small angular accelerations as well, right? We're not talking about a lot of torque here when we're changing, the hanging mass by 20 grams, and it's less than 2.5 centimeter radius, right, up that big pulley. So not a lot of torque here, but still a significant number, okay? Now, so this is what it means, really. It tells you how much the torque changes when you change the angular acceleration. But that doesn't really tell us kind of like where it comes from, right? Why is the torque in this case why is the slope in this case 0.0059? Well, sometimes the units can give us a bit of a hint, but only after we reduce them, right? And we can reduce these units. A Newton meter per radian per second squared. Well, what does this line actually mean? It means divide. So this is a Newton meter divided by a radian per second squared. Now, remember that a Newton is itself a derived unit. What does 1 Newton stand for? We did a whole lab on this, right, last year. 1 Newton is the force required to make a 1 kilogram object accelerate at 1 meter per second squared. A Newton is a kilogram meter per second squared in base units. They just decided to call that combination a Newton. Well, dividing by a radian per second squared is the same as multiplying by the reciprocal, a second squared over a radian. So if we plug those both in, replace the Newton with a kilogram meter per second squared, and multiply by the reciprocal, notice what happens. The second squareds cancel. The meters, remember these are meters, not mass, right? The meters combine. A meter times a meter is a meter squared. And the radian, because it's a name, not really a unit, just disappears. And so our reduced units are kilogram meters per second squared. Kilogram meters per second squareds. So let's throw that in there. Now you might be saying, well, how does that help? Well, kilograms are units of mass, right? And if you remember in the pre-lab, we said something about the mass, right, should have something to affect the amount of angular acceleration you get from the torque. But it wasn't just mass. And this shows that it's not just mass. It's also this meter squared, right? And meters are units of distance. Interesting. We will have to investigate that shortly. So the x variable in this case is the angular acceleration, and the y-intercept is essentially 0, right? If there's no torque, there's no angular acceleration. That's really Newton's first law, right? No torque, no angular acceleration. Can be moving, but it has to be moving constantly. So there's our equation. But let's talk about this slope a little bit, okay? Now, if you think about the related equation for linear, which is Newton's second law, which is net force equals mass times acceleration, the mass in that equation, remember, functions as an inertia, a tendency of the object to continue moving however it's moving, right? How hard it is to change its motion. Right? Something that's more massive has a greater tendency to keep doing what it's doing. Well, by analogy then, we would say that this slope should have something to do with the inertia of the rotating object, the tendency of the rotating object to keep rotating. So it's inertia, but it's not quite the same as linear, because it's not the tendency of the object to move at the same speed in a straight line. It's the tendency of an object to move constantly rotationally. So we call this the rotational inertia. It is denoted in an equation by a capital I for inertia. Makes sense, right? There is an alternate name that I put in here called moment of inertia. Some older profs, maybe more European way of saying it, rotational inertia is what you'd find in your textbook, right? But moment of inertia is acceptable as well. On rare occasions, you might see moment of inertia on an AP test. You have a ball rolling down a hill with moment of inertia this. Right? You just need to be aware that moment of inertia means rotational inertia. Okay, this thing we're going to spend several days looking at here. Okay, so operationally, the rotational inertia is the slope of the torque versus angular acceleration graph. Right? That's what we're going to call that slope. But more conceptually, it's the tendency of an object to continue in its same state of rotation, the tendency of an object to keep rotating the way it's rotating. We can also look at it as how much it resists changes in its rotation. Right? Objects with a greater rotational inertia will be harder to accelerate. Right? Harder to rotate. Right? And they'll be harder to start and stop as well, if you want to think of it that way. If I have a big boulder that I want to, and it's round, let's say, and I want to roll it right across the ground, if it's this big, large, heavy boulder, it's going to be really hard to start rolling. If it's a same size but it's made out of styrofoam, going to be a lot easier to get it rolling, right? So rotational inertia, however we end up calculating it here, right, is going to be how we talk about how difficult it is to start and stop it, the tendency to continue rotating the way it's rotating. So one way we can calculate it or find it is experimentally, as we just saw in this lab. Right? We can do a torque versus angular acceleration graph, and the slope is the angular acceleration. Is the rotational inertia. Okay? But how do we go about just figuring out the rotational inertia from the object, right? From how the object is set up or composed or how the masses are? Well, that is a process that's going to take us a good week plus to get through here. Right? It is not just as simple as mass. Everything in rotation is harder, and rotational inertia is a lot harder than mass. If we want to know the mass of something, we just drop it on a scale and mass it. Okay? Write the number in. We can't do that with rotational inertia. Okay? We have to do much more complex things. It's going to take us some labs, some derivations, even some calculus eventually to figure out how to calculate the rotational inertia of various objects, various configurations of mass. So that's something to look forward to here. But if we plug that I in for our number, we get a general math model, which is Newton's second law for rotation, the rotational version of Newton's second law. Net torque equals I alpha, where I is the rotational inertia and alpha is the angular acceleration. Or if you do one step, right, the angular acceleration is proportional to the net torque and inversely proportional to the rotational inertia. Okay? Inversely proportional to the rotational inertia. Now, I couldn't do that lab because we don't have a way to calculate the rotational inertia yet. So, I could have changed it, but I wouldn't have known what it was, right? So that would have been hard to graph. So we kind of had to come at it a little bit different than we did Newton's second law linearly. But again, notice the similarities. Net force equals mass times acceleration linearly. Net torque equals rotational inertia times angular acceleration rotationally. Now it has all of the issues that F equals ma does, but with all of the extra complications that rotation has. For example, torques are harder to calculate than forces, because not only do you need to know how much force, but you need to know where that force is applied. And as you're going to see over the next week and a half, rotational inertias can get quite complex to figure out, especially compared to mass, which is relatively simple. So for the next week and a half, right, we are going to be focusing in on rotational inertia. But we're going to use this idea of Newton's second law along the way for rotation, right, to help us figure out some rotational inertias experimentally.